experiment involves really trying to understand why protein crystals seem to form more perfectly in microgravity versus here on Earth. What I hope to see is not only really get a good understanding of the rate at which crystals grow in space versus here on Earth. We're comparing everything with ground controls that we perform here on Earth, but also to see if space can select out for the pure form of the protein, eliminating impurities that are always in protein crystal growth solutions. Microgravity is important because in space, without convective flows due to gravity that we see here on Earth, a crystal grows much more slowly. That allows the molecules to come together more perfectly. And the more perfectly aligned those molecules are, the better the quality of the crystal. And then when we bring it back to Earth, when we X-ray it, we actually expose it to X-rays, we see more detail in the three-dimensional structure of the protein, and that enables us to better understand how it functions in our body or in bacteria or viruses, and it also enables us to perform, in some cases, drug development. There's a national research announcement that NASA puts out for all scientists to propose against, and I wrote a proposal, and it gets peer reviewed by outside scientists, and they select the ones that they feel are most appropriate, the top proposals, and I was lucky enough to be selected. And so from that point on, it's a matter of just doing the work and eventually getting approved for your flight experiment. I think what excites me the most about this particular experiment, because I've flown others on the space shuttle and on the space station, all involving protein crystallization, is that we know we get better crystals in microgravity. The question is why? And this experiment is going to really provide a lot of the data to help us understand the multiple possible reasons that microgravity could be playing a role in producing higher quality protein crystals.